Yeah, hello everyone. Welcome to this week's Quant seminar. I'm Zhen Zhang. I'm a PhD student from the Quant group, and I'll be hosting the Quant seminar with Samtada in the next a few months. So today we have two talks, two speakers and two talks. Our first speaker is Dr. Alessio Alexiadis. His talk is about physics-informed machine learning using particle methods. Dr. Alexiadis is a lecturer in chemical engineering at the University of Birmingham, UK. His current research mainly focuses on discrete multiphysics and physics-informed machine learning. He has broad research interest, including photocatalysis, computational fluid dynamics, Barbie flows, multiphase reactors, etc. So without further ado, let's welcome Dr. Alexiadis for his talk.
Thank you very much. Let me start the presentation. Okay, so let me just move a few things around because, okay, this goes here. Okay, okay, my talk is about, well, thanks for inviting me, first of all, again. And my talk is about the use of particles, or computational particles, and how they can interact with the machine learning, in particular, how they can interact with the artificial neural networks. So wait a second, why it doesn't work? Okay, now I will start with a brief introduction to particle methods, very general, very broad, and very brief, just to introduce a couple of the ideas that will be used later on. Then originally I wanted to discuss a little bit something, an idea called the particle neuron duality. Particle neuron duals basically are mathematical function, but of course they are all mathematical functions, where they combine together certain abilities of computational particles to model the physics, to model a multi-physics system, and some abilities of the computational neuron to learn from data. But then I have second thoughts, in the sense that I don't think probably the presentation would have been too long. So I'm going to mention a couple of things about the particle neuron duality, just to give you, let's say, a very general idea and some reference in case you are interested. And then we can jump directly what I believe is the main topic of the talk, which is the minimalistic method. And I will explain why we call it the minimalistic method. Okay, let's start with the particle methods in general. Now you can think as in the more general, from the more general point of view, you can think of a bunch of particles moving in a computational domain. Now, if those bunch of particles are physical particles, which mean they are particles that they interact in a way that represent a certain physical system, well, they will obey an equation of motion. They will obey, for instance, the Newton equation of motion, which is here. I'm assuming that all the particles are non-relativistic, but in all practical sense, so we always have non-relativistic particles. Okay, and this equation actually works with any possible system, which is a physical system. The only difference between one system or the other is in the internal and external forces that describe the trajectory. What I mean is, let's say we have a particle, and the trajectory of the particle, it depends on the force that act on this particle. Some of these forces we can say that are external forces, like for instance the interaction between the particle and the walls of the computational domain. And other forces we can say that are internal forces. And from this point of view, we mean that internal forces are the particle-particle interaction. Each particle interacts with another particle or all around it, and each one of them exchange a force with the particle I, and the sum of all the forces gives the final force on that particular particle. Okay. So this is a very general equation, and every particle system must obey this equation. The difference between one particle system and the other is in the internal forces. For instance, if those internal forces are the typical interatomic forces occurring in a molecule, then we have molecular dynamics. We have a system, a computational system that can model the dynamic of molecules. if those forces are the typical contact forces that can occur among granules, for instance, Hertzian contact forces, for instance, in granules, well, we have a different physics. We have granular mechanics, and we have a computational method called the discrete element method, which actually describes this type of interaction. If the interatomic force, actually the interparticle forces are the gravitational forces occurring in stars, we use the same equation, but this time the internal forces is the gravitational forces. So very different system, but the same equation, only the internal forces they change. Now, when I'm saying particle, as a matter of fact, it doesn't mean to be a particle. It doesn't need to be a discrete object. For instance, in fluid dynamics, there is a method called SPH, smooth particle hydrodynamics. In this particular case, what we are doing, we take our continuum, we divide the continuum in a portion of matter, that we represent as particles. And if we do that, then we can use the same equation, but this time we have to make sure that the internal forces, they represent or they mimic the pressure and viscous forces occurring in the fluid. And the same goes for a solid mechanics. We have a solid body, elastic solid body. We can divide the portion of the solid body in computational particles, and then we have to make sure that the forces they mimic, they model the elastic forces occur in the solid. For instance, one way to do that will be to use the so-called lattice spring model. And what we're basically doing, we are joining the different particles with the computational springs in order to represent the elastic forces occurring in the fluid. Okay, so very general equation, and the whole difference every time is in the way we treat the internal forces. Okay, that is a very, very, very quick introduction to particle methods. Of course, all the details, all the numerical details there are a lot of the devils in the details, but anyway, this is a general overview. Given that, I will spend just a couple of slides on the particle-neuron duality, in the sense that if you think of a computational particle is, well, a mathematical function, and is a discrete, which represents a discrete mathematical object, and this mathematical object has some properties, like the position, the velocity, for instance, of the object, and exchange some sort of interaction with other particles, with other mathematical objects. But if we look at the particle from this point of view, we can also look at the computational neuron in artificial neural networks from the same point of view, in the sense that it is a discrete object, has some properties like computational weights, activation function, and so on, and exchange some sort of information with other neurons. Now, this information is not physical, it doesn't represent anything physical most of the time, but it doesn't really matter, because from the point of view of the algorithm, we're just sharing numbers. Some numbers for us have a physical meaning, for some others number for us, they don't have the same physical meaning, but that in principle, we do something very similar in the two cases. So the idea would be, okay, let's create a new mathematical object that has the property of both, that exchange forces, exchange information that represent force in certain cases, in exchange other type of information in other, which is not physically related in other cases, which are property like position, velocity, like computational particle, but at the same time as internal weights, at the same time as activation function, for instance.
Alessio, can I ask a question?
Yeah, sure.
This duality seems to be interesting, but here, for example, at least for this neural network that you have here, there's no lateral communication in this hidden layer, unlike the particles. Every particle on the left can. So we actually have something called with the Kronecker neural network, which we couple also the lateral. Laterally, not just forward as you have, but are you actually implying that you can have a duality between these particles which interact all to all on the left and these ones that don't interact all to all on the right, or that breaks the duality?
No, I don't know, in the sense, duality, when I say duality, is very general. every time, because if you think also in the terms of the computational particles, especially for this, the lattice spring model that I showed before, you decide which one are connected. You know, of course, it depends on the method. In certain cases, you just looking at what is around. In other cases, you decide which is the connection. So from the point of view of the general understanding of this duality, you can do whatever you want. It's just a very, very basic idea that you have this object that has a computational weight, a connection with others. Then it's up to you to how.
No, I understand that, but I basically what I'm saying is that the current artificial neural networks are not expressive enough to support this arbitrary, the physics, the duality of molecular dynamics, for example.
Yeah, absolutely. I mean, there is no one-to-one correspondence. I understand what you're saying, and actually, that is reflected in how we use that, because the way we use that, for instance, I mean, I suppose there are many other alternative ways to look at that and to use them that we didn't think about. But I just can tell you, given the limitation and partially the limitation we just expressed, how we use those duals in practice. Okay, most of the time we use that for the modeling of human organs. In the sense, you have your human organ, you do a model of that, and the human organ follows the physics and the chemistry. I mean, it should obey the laws of physics and chemistry. But on top of that, you have all the different complexity due to the fact that it is this time the real nervous system that interacts with the model to control some physiological stuff happening in your body. In this particular case, for instance, we have a segment of the intestine. And on the intestine, actually, there are sensory neurons that measure the stretch of the membrane. They communicate with the motor neurons that they contract the membrane. Now, the idea is actually to use an artificial neural network to model not the real neural network, of course, because they won't match, but just to model the input and the output, just to model, actually, just to mimic the effect of the real neural networks on the model. Okay, so we are not trying to model the neural system here, but just the effect on that. And the interface can be, the interface of that can be, for instance, the duals, because you can do your model with computational particles, you have your network, and then the interface between the two are those particles that at the same time they work because they exchange forces. They are part of the computational domain or the geometrical domain of the that we use for the modeling the membrane of the intestine, but at the same time they exchange this information with the network. The training of that normally is with the reinforcement learning, in the sense that we don't really know how it works the whole real nervous system, but we know most of the time we know what is the goal. For the case of the intestine, for instance, the goal can be mixing the food or can be propagate the food forward. So we know that, and based on that, we can we can have some sort of a reward function in order to train the network with reinforcement learning. But again, that is the way we're using that. I suppose there are many other ways. If you have now, I'm not aware of all the possible networks, of course, they are around. I suppose that it's even possible to probably to push these analogies, the duality, even further than that. Okay, I'm not going. That was not. It's just a deviation, let's say, from the main subject of the talk, which is the minimalistic. We call it the minimalistic approach to physics for machine learning. So let's start with a problem. We have a problem that we have a system. The system, let's call the system X, and the state of of this system is at time t is given by x of t, and the state of the system of a different time step, t plus delta t, is given by x t plus delta t. There is a model that allows us to go from x of t to x of t plus delta t, but we don't know the model, and we need to derive the model from the data. And well, we assume, first of all, actually, we assume that it's a multi-physical system, so it can be described with the physical equations. So the first thing we can do actually is to look if it's a particle system. Because if it's a particle system, well, we already know that even if we just see the system for the same times, we know that it must obey some form of particle equation of motion, like the one we saw before. If it's not, well, there is the chance that we can probably recast the system. Let's say it's a fluid dynamic system. There is a certain chance that we can recast the system as a particle system. If a fluid dynamic problem is a continuum, is not a particle system, but if you use a framework like the SPH framework, we can probably recast it as a particle system. If we can do that, so we go back to the fact that the model must obey to some sort of a particle equation of motion. Now, before I use the Newton equation of motion, which is nice to see how the forces are and everything, but in practice, actually, we have something much more general than that. And the Lagrange equation of motion is the same concept, the same idea, but in a more general way. And this is the equation. L is the so-called Lagrange, which is the difference between T, the kinetic energy, and V, the potential energy of the system. Q are the so-called generalized coordinates, which for us, if we think of point particles, for us are the X, Y, and Z coordinate of each one of the particles. And the difference between the Lagrange equation of motion, actually, you don't see immediately the forces like the Newtonian one, but they are there, of course. And the forces are divided in two groups. One are the conservative forces, which are the ones that can be expressed by a potential, and they're only function normally of the position. And then we have the dissipative forces, which are the Q term in the equation, when most of the time are just function of the velocity. Now, the difference between one system and the other, every particle system, which non-relativistic particle systems, must follow this equation of motion. The difference between one and the other, remember the atoms of the stars and so on, is this time now in the functional form of V and Q. If we know that, we can represent everything. An important thing is that actually inside the Lagrange equation, there is a lot of physics. Okay, in order to write that from first principles, we have to pack a lot, almost 200 years of physics into this equation. There are conservation of better generalized conservation of momentum, of energy are there. The state action principle, which basically is the one that allows us to write conservative forces as the derivative of potential, is there. The trajectory, the fact that the trajectory must be continuous, which is not given, it's not granted, but the fact that the trajectory of the particle must be continuous in space and time is there. So there is a lot of physics over there, okay? Just packed in the Lagrange equation, even before we start, let's say, do any type of modeling. So now let's go back to the problem, the original problem, and let's try a naive approach. We say, okay, we know the state of the particle of the system. I assume it's a particle system. We know the state at different time step, and we want to find out what is the model. So let's plug everything in a big network, artificial neural network. We can have millions of particles. You can easily have 10 million particles in a particle simulation. There are some very high performance simulation that use even billions of particles. So millions are really nothing special. So you can ideally say, well, okay, so each one of these particles here is the position of this particle, for instance, is an input for a huge network. And in principle, I mean, there is nothing wrong, in theory at least, to try this something like this naive approach. The problem is that by doing that, we are really asking a lot to our network. We are asking our network to rediscover, every time we use it, to rediscover like 200 years of physics history. All the principles that we already know are there. We already know are in the Lagrange equation of motion. They must be rediscovered every time. So, okay, instead of one alternative would be, okay, instead of rediscovering everything from scratch, let's use the Lagrange equation for the time evolution of the system, because any system must, any physical system must actually obey to the Lagrange equation. And the only missing part to the puzzle, the only missing pieces are the V and Q. So let's just use the network for V and Q, nothing else. And well, by doing that, we ensure that all the principles, the physical principles that I mentioned before, are satisfied in a strong sense, in a strong mathematical sense, are satisfied if we're doing that. For instance, even at the very beginning of the simulation, even actually if you just plug the random numbers for V and Q, well, you get a system that probably won't be the system that you're trying to model, in the sense that you won't be the system that you're trying to learn, but anyway, will be a system that is physically consistent. Even if you just actually that we are talking about random, even if you just really plug white noise, you get something that makes physically sense. If you plug white noise, actually you have Brownian motion in the system. If you don't, if you are not trying to model Brownian dynamic, that's not what you want. But anyway, it means that you have a system that still makes sense physically. Okay, so the goal is to just use the network for V and Q. There is an issue though, that we are going, that is the main point here, because in principle here, I mean, there is nothing fancy here. You have an equation, you just have some parts of the equation that you don't know, and then let's just use the network for those parts. But there is a little issue here, a little annoying issue, is that there is a mismatch between the data I have, the data I have from the state of the simulation, and the data that I need to train the network. So I have a certain type of data, but it's not the type of data that I would need to train the network. And in the next slide, we're going to see why we have this mismatch, how we can solve that, and we gradually introduce some of the ideas of the minimalistic method. And then we're going to do that through 3 examples. One is an example from molecular dynamics. We use that for introducing the basics, basically. Then we go to a fluid dynamic system, which is dissipative. The molecular dynamics case is conservative. And then we use granular mechanics to discuss how we can actually extract from the system, but also the boundary conditions. And to do that, we frame the problem as a reverse problem. So we can we have 3 simulations. One is a molecular dynamics simulation, the other an SPH simulation, the other a DM simulation. I know everything of the simulation because I produce the simulation, but the network doesn't know anything about the simulation. So I have to extract all the physics from the data for the output file. Now, first of all, actually, we have to mention what are the output file, in the sense that the typical output file of a particle simulation, it can have position, velocity, and acceleration of each one of the particles. Now, there is a best case scenario and a worst case scenario. In the worst case scenario, you only have the positions. And actually, typically, for instance, in molecular dynamics simulation, you are the output. If you take a random molecular dynamics simulation and you look at the output, typically you only have the positions of the atoms. Sometimes you can have the forces, the overall force of each one of the atom, which are the accelerations. Here, I'm going to use force acceleration in interchangeable way, simply because they are only rescaled with the mass. Even if you don't the mass, you know they are rescaled. So you can just say the mass is 1 and then you rescale everything the force. So basically, when I say force or acceleration, from a certain point of view, it's just the same type of information. And in SPH simulation, you have the position because you always have the position. You always have the velocity, almost always the velocities, but you don't have the forces, you don't have the accelerations. In DM, you have the positions. You normally don't have the, sometimes you have the velocity and also sometimes also the forces. So it really depends where, from case to case. But in general, again, you have the worst case scenario when you have only the positions. If you are in the worst case scenario, and you have the simulation, you can actually extract the velocities from the positions and the accelerations from acceleration from the velocity. It will introduce some numerical error, of course, by doing that, and that's why it's the worst case scenario. And we have done some checks to see if the method is robust to a certain level of noise. Results are encouraging, but it's not a systematic analysis of the noise. So I'm not going to present it because it's not a systematic analysis. So just to make things simpler, I will consider them in the base case scenario, which is the one when I have the position, the velocity, and the acceleration on each one of the particles as a typical output of the simulation. If not, you can actually have everything, recalculate everything, but of course you may add some numerical uncertainty in your results. Okay,
hi,
now,
Alessio.
yeah.
Hi, this is
Hi.
Milan at Brown. I have a quick question. If you can go back to your previous slide.
Sure. This
So
one here.
so why do you call this reverse problem or instead of inverse problem? I think there is a
or it's just possible it's a typo, to be honest. Yeah,
okay.
yeah, you are right. I should write inverse.
Okay, yeah, thanks.
Yeah. Thanks for noticing that. Whatever. Okay, yes. Now I'm going to briefly now mention how we run the molecular dynamics simulation, just so we know what is the physics of the system. This is actually this is what the network doesn't know. That we know everything because we run the simulation, but that's the network doesn't know anything about that. So, but I think is important actually to have a little overview of the physics of the simulation, because based on the physics we are going to see some parts of some ideas of the methodology. So in principle we have a conservative system, no dissipation, and then we only have conservative forces. Normally, which are actually the derivative of potential. Normally, the potential is expressed as a sum of different parts. The first one, it just depends on the position of the particle. So you have, like gravity, for instance, any external field can represent just as a potential function of the position of the particle. Then you have pair potentials, and the pair potential normally depends on the interaction between pair of atoms. And therefore depends on the relative position of two atoms at a time. Then you can have three body potentials, which depend on the relative position of three atoms. For instance, if you are calculating the force over the particle I, it will depend on the relative position of K and two other atoms like K and J. And you can think of that a little bit like the angle in between that. It's a possible three body potential is the angle. And then we can have four body potential, five body potential. Actually, you can have multi-body potential and so on. Now, there are like hundreds, if not thousands of potential in molecular dynamics. The 99% of them are pair potentials, and 99% of the simulation are based on pair potential. So to make things simpler, here we only consider pair potential, and we are not considering multi-body potentials. On top of that, in this particular simulation, in the molecular dynamics simulation, we are not considering any external field. We're going to see that the gravity in SPH case in the granular mechanics problem, but for the moment we only have the pair potential. And in particular, we use in our simulation a very, very common potential, which is the Lennard-Jones potential. Basically, this is the formula. It depends on two constants like epsilon and sigma, and then Rij is the distance between the two atoms. And yes, and let me introduce actually in this potential another concept which is going to be very useful later on when we discuss neighborhood list. Now, all four, when it comes to physical particle system, they all have something in common, and what they have something in common is the larger distance between particles, the less is the force, the interaction force between the particles, which means that as the particles, the distance of the particle is above a certain cutoff radius, they don't see each other anymore. They don't interact anymore. The force is zero. So we just have to look at what happens around the particle, a certain distance, a certain cutoff radius, but not further than that. If we do that, we have the force. It can be expressed as a vector. This vector actually depends it has the same direction of the distance between the two particles, and this is the V or either in the Lagrange equation. So either the force or the V, they are related, of course. And is a vector, but because I know the particle position at every time step, I know the particle position, so I don't really need the vector. I only need the magnitude of the vector, basically, and therefore this f, the small fij, is what I'm looking for with my artificial neural network. And okay, we run this, we put some numbers in our simulation, and this is the simulation we try to learn. So this how it looks. It's two-dimensional. It won't make any difference if it's three-dimensional, so it's easier to make it two-dimensional, just that. Something actually can be worth mentioning here is the temperature. The sense that from the point of view molecular dynamics, the higher the temperature, the more particle move, because it's the kinetic energy, the average kinetic energy of the particles. And so the more energy they have, the more collisions you actually will see between the particles, and therefore probably the particles will get closer during the collision. It's something actually we're going to use later on.
Alessio, can I ask a question here?
Yeah,
because
absolutely.
I think you assume a homogeneous system, periodic, so you don't have any walls, because then you would need a different V.
Yes, of course. Actually, I'm not using here, I'm not discussing the boundary condition on purpose, because I'm going to discuss the boundary condition with a third example. So yes, the boundary.
But in general, it's possible to have a heterogeneous systems with different V, searching for different V's, potentials.
Yes.
Okay, close to the walls and close to the bulk. Okay, sure.
In all the three examples that I have here, except for the boundary conditions, I'm using homogeneous systems, in the sense only one. If we have more than one, we need to have a different potential for each one. So let's say we have two particles, blue and red. So you need to figure out what is you need a network for the blue-blue interaction, you need a network for the red-red interaction, and then you need a network for the red-blue interaction. So we'll need three. Okay. Okay, now let's introduce the concept of the neighborhood list, because actually that will also explain the mismatch between what we want and what we have. Now, because we know that above a certain distance particles, they don't see each other, we have a radius, and all the particle I interacts only with the particles within this radius. The particles in this radius are part of the neighborhood list of the particle I. And the resulting force of acceleration over the particle is the sum of all the forces only within the neighborhood list. Now, the mismatch is that in my input data, in my data set, I have, in the output file, I have this information. I have the final acceleration or the final force. Again, I'm using that in an interchangeable way. So that's what I have in my data. But if I want to train for V or Q, in this case V, that's what I'm looking for. So there is a mismatch because I don't have the data that I want for training my network. Okay. So, and that's why we have a mismatch. So if we look at, in general, we can play around that by modifying the loss function. So traditionally, it should be the loss function that we have the target and then the output of the network. But we don't have this one because the network has this F actually. So we can just make a substitution here. Instead of calling the network only once, we have a different network, and we need to call this network every time for each one of the neighborhood list. And we can actually calculate the neighborhood list. It's not a problem because we have the position, and we only need the position of the particles to recalculate the neighborhood list every time. And this actually is the loss function for a single neighborhood list at a single time step. Then we have to put everything together, which means that we need to add all together all the losses for all the neighborhood list n. We have n particles. Each particle is a neighborhood list, so we have to sum all the n neighborhood list. And then for all the the NT time steps. Now I'm cutting a little bit of corners here in the sense that I'm not going. I really don't want to go into the several details, but just generally, if you just look at this loss function here, the problem is ill-posed in the sense that actually you won't be able to invert this one. And the way why it works is because when you add everything together, lots of the neighborhood lists, they overlap. What I mean is that you can see here there is the force between I and J, but then when you have the neighborhood list of J, you have I again. Thanks to this overlap, so the fact that the same variable is repeated in many neighborhood lists, you can solve actually this problem that otherwise would be ill-posed. Okay, let's solve it. So we use this loss function. We have a network which the input is Rij, which is the distance between the atoms. The output is the force of the pair for each one of the pair. And honestly, we just give a little try and error. We found a network which works, and we stick with that. Very small, so as you can see, it's a very small network, so easily trainable. And training loss, validation loss, very low. And then we can.
Alessio, can you give us a little details, because we are all interested here in this group on
yes, sure.
MD and DPD and so on. So we know the details. So just give us a little bit of, like, NT could be 1,000,000, but what do you take here, and the number of time steps?
What do you mean? So INT. Okay. In this case, because this system is ergodic, the molecular dynamic system is ergodic, which means basically that you are going to is conservative, and therefore is going to move in a certain area in a certain area of the state space almost in a uniform way. So really, you don't really need all the. What I'm saying is that you can have actually millions of data, but you don't need all of them.
Right. What did you do?
You just take some of them. If they are too many, you just throw them away.
Sure. Just tell us what did you use for NT?
I don't remember. Is because actually I'm taking it's like 1,000. I don't remember, to be honest, but it's not a big number in the sense that the simulation has many time steps, but I just take one every. I don't know, something 100, 1,000, something. That is the order of magnitude anyway. Now I don't remember the precisely, but that is the order of magnitude.
Okay, and then N is, how many molecules do you have here in this system?
There are. Wait a second. Let me go back. This says.
Okay, the neural network is small.
Here is 320.
Okay, 320. Yeah. Okay.
Okay.
Small system. Yeah. Very small.
Yeah, it's a small system actually. Is just to test that.
And sorry, can you explain the how do you get the target? Is that just like a finite difference thing?
The target, no, the target actually is given from the output file of the simulation. In my simulation, remember they told you, in my simulation, I have the positions. This is my, you can have the position, the velocities, and the accelerations. So the target are the acceleration. If I don't have that, I need, when I mentioned before, I need to recalculate from the positions. It will have some numerical error, but that's why I'll get the target.
Not given, and not join a little slow later because he didn't have the link. I just sent to him. Not, he assumes that he knows the MD data. Given is the MD data.
Oh, so you're just querying the linear Jones.
Yeah, he's trying to learn the Fij. Yeah.
Yeah. Okay. Thank you.
He's trying to learn potential energy, basically. That's all.
Yes, exactly. Okay, so this is the system, and then we can compare the potential energy with the training one. And what we see here is that it works well. And then we have an untrained region here, which doesn't work that well. But actually, the reason for that is if you look at what it means here, is that particles, when they are closer to a certain distance, they are not, the potential is very different. But if you look at the system, normally particles, they don't get that close together, which means that the reason for that is because the repulsive forces here are strong enough to avoid overlap of the particles. So we don't really have any particle overlapping above, and therefore there are no data.
But hold on a second, because here you learn the wrong potential. You learn the repulsive potential only.
No, it's everything. It's everything. Here you don't see that, but this is everything, because this one is the force, right? By the way, this is not the potential, it's the force generated.
Oh, okay. So it goes below zero. So you get.
Yeah, it does. It's not very high. If you write in the dimensionless numbers, you have one.
Your RC, Alessio, your RC was 2.5, and you only go to half of it. Did you have the rest of it?
Sorry?
Your RC was 2.5. I saw that in the.
Yes.
But you only go show half.
No, but okay, is okay. It goes. And I just showed that because it was flat. But it goes.
It should go up again.
Eh?
It should go up again to from attractive, come back to repulsive.
The repulsive, yes, it goes up. I mean, that is is 2.5. Actually, is the I probably just cut because I just cut the picture, but he has the correct one. But anyway, consider that if we put 1 and 1, you don't see a lot. I mean, in the force actually, what is the minimum? This is the force. So what is the minimum in the potential is the 0 of the force.
Yeah.
Okay, so here you are not seeing the nice peak below, because it's the force, it's not the potential.
Okay.
Okay.
Thank you.
But anyway, since you mentioned that, this is important because I forgot. Now, of course, when you run the training, you don't know when you run the simulation, you impose the cutoff, right? And when you run the training, you don't know the cutoff that's been used in the simulation. There's not an information you have. But this actually is not a problem, as a matter of fact, because you need to reconstruct the neighborhood list, but you don't know the cutoff that's been used in the simulation for reconstructing the neighborhood list. But it's not a problem actually, because as long as you have a cutoff which is longer than the real one, the system automatically understands the sum of the particles which are far away. The potential is 0. They are no use. Right. So the only thing you have to make sure that you have a cutoff. So you have to go big in a way. So you need a cutoff which is for your training, which is larger than the one that's been used in the simulation. You don't know that, but normally, I mean, if you use a large one, then if you use a shorter one, the results actually are gradually worse and worse. But if you use a large one, the system automatically understands how to take out particles they are not using in the overall sum. Okay, let's move to the small particle hydrodynamics here. So here is the equation of motion. And then here we have a pressure force and a viscous force. W is a kernel, which basically again gives you the same information of the neighborhood list, in the sense it tells you that when particles go far away, the effect of the force are less and less above a certain threshold, the cutoff. They don't see each other. And then in this case, actually, we'll also add gravity in the system. Now, just mention some. There are actually very many formulations for the pressure and viscous force in SPH. I use very simple one, let's say. And in particular, actually, the viscous forces now depend on the relative velocity. And in particular, actually, they depend on the relative velocity, but in the direction of the approaching or diverging particles. And in our molecular dynamics case, we were trying to learn Fij, which was only function of R, but here it will be function of R and the velocity. The velocity is the dissipative part. Now, as you can see here, actually, we also have some additional, when it comes of the SPH, we also have some additional variables. And those additional variables are like the pressure and the density of the particles. Our pressure and density, not in the molecular dynamics sense, are just numbers. Okay, we're not calculating that. It's just variables that we attribute to each one of the particles. And because we give this new variable, we also need to express the evolution of this particle during the simulation, and we can do that and there are some expressions also for that. Now, it's important to note that those are all internal variables for the SPH method. The network doesn't need to know anything about that, in the sense that the only Lagrange equation approved input of the function of the network here are the positions and the velocities. The rest is everything are things that are internal to the SPH case, but in principle we don't need that, because it's the way the SPH works to figure out the pressure and the viscous forces. Okay. Now, there is a small issue here, though, because if you look actually how the density is expressed, while if you look at the pressure force and the viscous forces, they are expressed as a pair potential, the density is not. The density is a multi-body interaction. Is a sort of average. So we can solve the problem in two ways. One, it will be just to reformulate the whole system, let's say the whole method for non-pair potentials. And that's something actually is left for future work. And the other would be to cheat a little bit in the sense that if you look, we added the density for the particle I and J in the network as an input of the network. Now for SPH, that's not a problem, because actually when you run SPH simulation, you always, as an input for output file, you always has this information. So we are not really cheating in the sense we have this information for the output file. Always happens. But if we are trying now to reverse some data coming from experiments, for instance, let's assume that you have a PIV experiment, particle image velocimetry. Well, so you have those particles, and you say, okay, let's see how we can extract some sort of physics from those particles in the flow dynamic experiment. At this point, no. At this point, actually, you have to be more rigorous, and you have to extend the method to non-particle potential, to non-pair potentials. Okay. So here the easiest way to go around that is actually to just add the row in the network. So now the network is a.
Sorry to interrupt. So yeah, you can go back to the last slide, please.
Yes.
So in SPH, there's an important variational derivation that connects the effectively the pressure gradient to the equivalent continuity equation. So when in the forward version that's not data driven, it's important that you choose the pressure gradient just right so it's consistent with this density summation. And that puts a constraint on your dynamics. And if you want it to actually to be consistent with the Lagrangian, okay, there's this structure preservation that you have to get right here. And it makes, what you're doing makes a lot of sense, but you're violating that constraint. So you're losing
what constraint do you mean?
If you start from a Lagrangian of the Lagrangian for multiparticle dynamics, and then you assume this density summation, once you go through the Euler-Lagrange equations, it restricts the form that the pressure force can take. Sort of in the same way that, like, you have a divergence in a continuity equation, and that's adjoint to the gradient operator that you get from the pressure in the Euler equations.
Okay, I'm not sure if I understand 100% what you're saying, but from this point of view, because the density are from the output file. So the value of the density should square everything from this point of view. Not sure if I'm answering your question.
I guess what I'm saying is that your data, what you're doing makes sense, and the data, the inputs and the outputs, and I'm sure that you can learn trajectories, but I think you're losing a lot of the structure preservation that's important in traditional
yes,
SPH
okay,
stuff.
yes, okay, yes, actually, I mean, I understand what you mean now. Yes, actually, we don't use this system. Actually, it's not to extract feature from. It's a different problem. Now we are looking at from the point of view of the inverse problem, but we are not looking at for extraction like macroscopic feature of the flow, for the simple reason that all the interaction actually are in this case actually a pair interaction. So yes, you lose but the method is not meant the complexity of the fact that you have macroscopic structure in the flow. It is there because of the way that the small interaction act together. Is a consequence of a larger scale. We don't see that from here, because here is like the fundamental physics, if you want. Did I answer this time your question?
Yeah, maybe we can follow up offline. I don't want to slow this down, but what you're losing, for example, is a stability theory that's attached to it, right? So if you do long-term integration, you might get a good fit for short-term trajectories, but for long-term integration, it might blow up. If you're not careful to observe those structural constraints. So happy to talk off.
Okay, anyway, yes, there is something about the trajectory later on, so we may come to that later. Okay, this is the network again, and training, validation. We have something similar as before, in the sense we have a training region and an untrained region. Here, this happens when we have particles very close to each other with a high positive velocity, which means particles, they just bounce back because they are very close together at a positive velocity, so they are bouncing back, and the velocity is very high, which is not really something happens normally, because if you are just bouncing back because they're close together, normally the velocity is just reverse the velocity, so it's normally is small. So it's an untrained region because simply because this situation doesn't normally happen. Okay, now on the left we have the original SPS simulation. On the right we have the one that used the artificial neural network potential. Okay, and we compare that. Now, all particle systems are chaotic by definition, the butterfly effect and all that. So that's not important, the single trajectory, because anyway, the single trajectory of two particles, if you compare the single trajectory of a single particle, actually they will diverge. Sooner or later they will diverge. That's by definition. What is important here is the overall, it's not the single drop, let's say, but what is important here is the overall macroscopic, the rheology of the fluid, actually, if we want to look at that. So the overall features of the fluid are important. For instance, how I don't know, how tall goes the splash, the fact that you have a certain wave in a certain manner. This is the rheology of the flow, the macroscopic rheology, which is generated by all the small and particle-particle interaction. If you are just looking at the single trajectory, you may see that the single trajectory diverges at a certain point because it's a chaotic system by definition. Although here there's dissipation, so it helps a little, but anyway. Okay, so you can see that here the main feature, there are some droplets here and there, they are different, but the main features of the flow are captured. Now, how can we generalize how generalizable are the results? Because actually here we capture the potential, we capture the physics, okay? So let's try to use the same model, we capture with the artificial neural network, which we train with the water column, okay? So we train with the water column, and then we use the same model. We don't retrain the model. It's the same model that's been trained only with the water column. And then we check how does it perform with a completely different system, which in this case would be pipe flow, okay? And you have some sort of pseudo turbulent behavior. I'm not going to discuss why we have that anyway, but it's not important why we have that. We have this sort of pseudo turbulent behavior, and therefore again, because the system is chaotic, if you just look at the trajectory of two of the particles, at a certain point you will diverge. But if you take a macroscopic, like you take, for instance, the velocity profile, the time average velocity profile in the two cases is very close. I mean, is almost the same in the two cases. Okay, but actually, what is important here is the training, the network was not trained for this case, was trained for the other case, and but still works, so it can be generalized to a completely different scenario. Okay, now the last one, which is the discrete element method. And in this case, we have particles, real particles, which are interacting with each other. So, and when they interact with each other, when there is a contact between particles, we have two types of forces: the conservative forces, which is the elastic forces, and the damping forces, which are the dissipative forces. So the situation is very close to the one before. In this case, we don't need density on everything. We can just go with the Lagrange equation approved variables, which are the only one in theory we should use. And so it's very similar to the other one. But the difference here is that in this case, we also going to consider what happens on the wall. So we are considering now the walls are reflecting. So we are going to look at what happens, what type of we don't know the interaction between the particles and the walls. So we assume that there is, again, also in this case, we have contact, Hertzian contact, we have the dissipation, but it's a different model. In the sense, actually, the model, the functional form is the same, but the numbers are different because are different. The wall is made of a different material than the particles. So the way to approach that is to use a second neural network for the boundaries. And in this particular case, we have a network that we call it WANN, which is actually the neural network for the wall. and which we depend on, which has its own, we depend on the distance, let's say, and the velocity with respect to the particle I and the boundary B. The principle is the same, but of course the model will be different. Now, how do we apply that? Well, first of all, we look at the bulk in the sense that first of all, we look at the boundary, the neighborhood list, and there are some neighborhood lists that are only within the bulk. In some neighborhood lists, there are only particles that they interact with other particles, no boundaries. While we have the other neighborhood lists that interact with the boundary and potentially also with other particles. So we start with the neighborhood list that only interact with the particles. And in this case, exactly the same as before, nothing changes. The only difference here is that I'm not using all the n neighborhood list. I'm only using the n minus b when b are the neighborhood list which actually interact with the boundary. Well, after I'm doing that, I know now the model for the particle-particle potential or force. After that, I can move to the boundary. Now I still have the mismatch. Actually, here the mismatch between the data that I have and the data I want is even stronger because now everything is together. It's both the particle-particle interaction and the wall-particle interaction. But because now we have a model for the particle-particle interaction, we can take it out from the force, and now we can train only for the wall interactions. So in this way, now we have the wall interactions. So again, this is the network when we use it, more or less the same in both cases. What changes, of course, is the loss function, because this loss function will depend on this on the other model. And now on the left you have the original one with just the dm. On the center you have we calculate the interaction with the model only for the artificial only for the particle-particle interaction. But we use for the simulation the real boundary conditions. In the one on the right, we use both. We have both the bulk and the boundary conditions from learned the same from the data. And at the beginning there is gravity, and at the beginning there are some random number for the initial velocity, which of course are random, but they are the same for all of them. Okay, so again, as we normally have in case of particle simulation, normally trajectory, the system is chaotic, so after a while the trajectory will be different, but slightly different. But if we look, for instance, how the kinetic energy changes, at the beginning they all overlap, and with time you can see some difference of that. So sooner or later it will diverge, because actually in a real system they will, if you repeat the same experiment twice, you will get a different configuration because of the. But if you look actually at the, in this case we cannot call rheology, but the overall granular behavior, you will see that you capture the overall behavior. Okay, now let me. Now I just want to re-stress the same things, but from a different angle, if I still have time. Do I have time, right? I have 3 slides when I want actually to
yes, Alessio, you can go on.
Okay, so what I want to show here is a little bit what happened now I present everything. I'm a mathematical modeler for training, let's say, so I'm not coming from data science, so I present things from the point of view of the mathematical modeler. But now I just want to change a little the angle and to look at it from the point of view of the neural network. So in the naive approach, what we do, we take all the particles, each one of the particles is an input of the network, and you can have millions of particles. And actually, in theory, actually, the input of the network is not just 1 per particle, but is 1 times the degree of freedom of each one of the particles. So in 3D will be 3 times n. In 2D, 2 times d. So it's even more than that. But just for graphical representation, we have a network like this one with a lot of which can have 10 million particles. Now, what we are doing when we do the neighborhood list, and we use the neighborhood list here, we don't look at all the particles, we divide everything in neighborhood list, and we just look, and we look at all the neighborhood list, but we take advantage of the fact that each neighbor list must have the same physics, must respect the same physics. So basically what we are doing here, we are taking our big network and we're breaking the network in small pieces. And then we realize that each one of the pieces must follow the same physics, the same model. And therefore we can reduce the input of our network from N to NL. And then everything the output is the force, and this force actually is plugged into the Lagrange equation, which gives me the evolution in time, rather than try to model the evolution in time with the network. Okay, so in this way, actually, we can reduce the number of inputs from N to NL. And normally, while N can be millions, the number of particles in a neighbor list normally, well, it depends on the method actually, but in molecular dynamics, I would say is around 20. In SPH, sometimes they're larger, you can be 30 or something. In DM, it's very small actually. In DM, you normally have 2 or 3 particles in the neighbor list. So you sensibly, because of that, you reduce the size of your network. But then, if we also, beside the neighbor list, we also consider the fact that they are all pair potentials on top of the neighbor list. Actually, what we are doing is we're looking at each one of the single potentials or the single pair for. So we are taking our network and we're still breaking the network even further, okay? In such a way that now we have a very small network which represents a single interaction, and that's why we can minimalistic. In the sense, we are looking for the minimal network that can solve my problem. And of course, the mismatch is in the fact that this is the minimal network is at this level, but the data that I have is at this level here. So the training level is not the same level of the network, and so therefore that's why we need to use this different loss function. Now, one thing that actually can be surprised at first glance is the fact that while all the information that we have, we kind of distill the information in neighboring list, it seems to be asking for some sort of convolution here, right? It seems to say, okay, because most of the information depends what happens around, so it will look natural that to use some sort of convolutional layer. But actually, we don't have any, we don't need any. And the reason for that is that the neighbor list has the same effect of a convolution in practice. As a matter of fact, it plays the same role in the sense that it takes into consideration the fact that actually there are all the neighbors around, and all the information of the proximity is there. Not only there, but is already optimized, if you want, from the physical point of view. I already know from the physics that I need to look at the neighbor list.
It's going to do a paper review. The paper is about equivariant graph neural networks and equivariant graph neural flows. So, Zhen Zhang, you may want to take over.
Yeah. Okay. Thank you for the introduction. Oh, can you let me as a co-host?
Oh yeah, sure. Just a moment. Yeah, I think you can share your screen now.
Okay, good. Can you see my screen?
Yeah.
Okay, yeah, sounds good. So hello everyone. Today I'm going to give a brief paper review of this paper, EN equivariant graph neural networks, and also the EN equivariant graph normalizing flows. And this is a paper done by a research group at Netherlands. And I think they are from the University of Amsterdam and the Microsoft research. So yeah, so let's begin. And to give a brief overview of this approach, I start with some background materials, that is the graph neural networks for the particle simulations. So here, like we are doing like a similar thing as what Dr. Alexiadis, what they do is similar to what Dr. Alexiadis is doing. And so basically the goal is to take an input of a particle system, a snapshot of a particle system, and trying to predict the next snapshot of this system, right? So, but the difference is that what they do is they utilize this type of graph neural networks. And what does these graph neural networks do is that it first takes the input X here, which is like a snapshot of this particle system, and it goes through an encoder, basically construct a graph based on these positional and velocity information of the particle system, and then it went through a set of graph network layers, which do the message parse between these nodes. And so through several of these graph networks layers, you get a final output, which called GM, and you send it through a decoder, which is another neural network, to extract the dynamics information. For example, you can extract the acceleration or velocity or any other quantities to help you predict the next step. And this is basically DeepMind has utilized this approach to conduct the particle simulation based on the data that is simulated from either SPH or other more complicated simulators. And here are some video demonstration to show some of the results that can already be achieved through graph networks. And because there are a lot of these animations, I will just pick some simulation that I find most interesting. For example, here you can see by using this kind of a graph network structure, you can really handle the multi-material simulations based on the data simulated from NPM. And another advantage of using this type of data-driven method is that you can train the neural network from a small data set. For example, you can train the neural network on a data set of 2.5K particles with 600 steps, but you can do the generalization task on particles or more particles and more time steps. For example, here you can do the generalization on a much more complicated scenario, like the water vortex, even though you are just training it on some simple domain, and something even trickier, like this. So basically, the training set is the same. The training set is something like this. Based on this simple training set, you can do the generalization on much more complicated scenarios. So yeah, this is just a brief overview of what this type of graph neural networks can achieve. And actually, they have given the open source code, so we can so anyone who wants to do research in this area can just go to the GitHub page and just do some plug and play experiments. And so here is the graph neural network architecture that they utilize to do this kind of simulation. And so basically a graph network, as I just described, is composed of encoder and processor and decoder. And this processor is composed of several different graph convolutional layers that maps the HL to HL+1, where HL is the latent node feature. And so what the graph network does is just to take these latent node features and also the AIJ, which are age attributes. For example, in the molecular dynamics simulation, you have this kind of this type of spring constants, for example, to represent this AIJ, and also. So you can send this through a neural network called phi-E to a value MIJ, which are the updated age attributes. And then you do an aggregation for this MIJ to get an MI, which is the new node feature. And finally, you send it through another neural network to get the latent node feature in the next layer. So actually, if you just have one layer here, then it is kind of similar to what Dr. Alexiadis was doing. Is here the MIJ is basically the force that you are learning, right? But why do we need why it is beneficial to have several graph layer here? It is because for example, in the SPH modeling, you want to, sometimes you don't know this rho I and rho J, And these type of things can actually be calculated from, for example, the positional and velocity information, so that you need like, for example, one layer do the message parsing and do the aggregation to give you this kind of row I, row J information, and then you pass it. So then you save it as, for example, HL+1, and then pass it to the next layer. So I think that is why like graph neural networks can be very powerful in this type of modeling. Yeah, and so so this is basically the architecture for the processor or the intermediate layer of this graph network, and then for the encoder and the decoder, it is what they do in the literature is that they normally just construct the graph by assigning a node to each particle and then create edge between particles with distance less than or equal to a constant r. And the graph can be dynamically constructed in the sense that because you want to make the prediction of this particle system, so every time you get a different velocity and positional information, so that you have to update this graph based on the distance between these particles in every like time snapshot. And two neural networks are used to map the node and edge features to the latent space. Basically, you want to map the position and the velocity x and v to a latent vector hi0, because you want to basically the meaning of this encoder here is like you want to write in a good coordinates so that you can infer better. So that's why you need this kind of encoder here. And so at the last layer, you have a decoder in the sense that you need a neural network to decode the last layer output to the final result. And for particle simulations, this yi could be the output could be the acceleration at the current time step. And then based on this yi, you apply, for example, a numerical integrator to give you the position and velocity information in the next time step. Or it can be just directly output the result at the next time step. So both cases are doable. And so this is for particle simulations. And so these graph networks can not only be used for the particle simulations, it can also be used for other tasks. For example, if you want to make some predictions whose output is global, in the sense that, for example, if you have an input which is the positional information of a molecule, and if you want to predict its chemical properties, so you don't want to predict this motion in next time, so you want to predict something global like the next the chemical properties, you can simply apply an aggregate function on all nodes to give you a global feature, so that you can use that as the final output and design a loss function. So both cases are doable. Yeah, and here is some of the things that I find like very interesting, in the sense that based on that DeepMind paper, to utilize the graph neural networks to do the particle simulations. So people may ask, like, why do we need to use graph neural networks? Why don't we just use the existing methods, for example, like SPH or MPM or something like that? So they compare like the computation time with using the neural network with that of the traditional methods, for example, like the SPH. And they actually show that they can really achieve like an acceleration or like a speed up of these type of experiments in a lot of scenarios that they are considering. Basically, the videos that I have just shown so far. I mean, just now. So here on the last column, in this percentage so this 0.071 means that for one time step, to roll a one time step, they need this amount of seconds to move one step forward. And the percentage means that the amount of time compared to the traditional methods. But note that here, they didn't compute the neighborhood computations because they say that they are not experts in the particle simulation. So their implementation of the neighborhood in computation is not very efficient. So they think it's not very fair if they take that neighborhood computation into account. So, but still, I think they show some kind of prospect in terms of using these graph networks in molecular simulations, in the sense that potentially you can really achieve some speed up using this type of approach. Yeah, and so now let's go to the what this equivariant neural network paper does. So what they do is like they introduce like a very simple idea into the existing graph neural network approach, and so to do some simulations based on that. What's that simple idea is that so to model the molecules, there are a lot of symmetries that people can take consideration into. For example, this equivariant feature, like so a function phi is called equivariant to Tg if phi Tgx is equal to Tg phi x. So that may be a little bit abstract, but if you break it down, like, so here are two specific examples. You can have translation equivariance, which means that if you, let's say, for example, here x is the position of your molecule, and then you translate it by a constant g, and then you apply a function phi onto it. This phi could be the flow map in the physical domain. So for example, here x is the position of the molecule at this current time step t0, and you want to predict the position of the molecule at next time step. So this phi is the flow map from t0 to t1. And then you notice that this kind of flow map is equivariant to the translation, in the sense that if you move your particle to the right or to the up or to any direction by a constant, then then when you move it move it forward in time, it's not like you translate it and then move it forward in time. It's the same as you move it forward in time and then translate it. So this is the message. This is the main idea of this translation equivariance. Also, the same thing for the rotational equivariance, in the sense that if you rotate your camera angle by a little bit, then it doesn't affect like the physical ground truth where this particle will go. So they also have this kind of a rotational equivariance feature. So they want to incorporate these two equivariants into the graph neural network, which has already have the intrinsic permutation equivariance. So basically, for a traditional graph neural network, it is already permutational equivariance, in the sense that if you permute your coordinates, if you permute your particles, like you switch the ordering of the first particle and the second particle, you are just changing the label. You are not affecting like its chemical properties, or like you are not going to change what the result will be, what the position of this particle will be in the next time step. So basically they want to achieve these three equivariants together in a graph network. And what they do is really simple, in the sense that they just change the original graph convolutional layer in the processor I just described into a so-called equivariant graph convolutional layer. And their input will be the XL and HL, where XL is the position, it means the position of the particle, and HL is the latent node feature. And the only difference here between this approach and the previous one is that between this approach and the original one is that it takes this XIL minus XJL, which is the distance between particles, into the input of the neural network. And through that, they prove that they can achieve this so-called EN equivariance, basically translation equivariance and permutation, and rotational equivariance, in the sense that QXL plus 1 plus G HL plus 1 will be equals to with each equivariant graph convolutional layer acting on QXL plus G HL. So this is pretty simple idea, and it actually achieved this equivariance. And so also,
hello, Jen.
yeah.
So for the here, it seems to me they miss, if we only use the relative distance, we miss the information of the angle. Do we?
So no, because like here you also do
Oh,
mean like
okay.
So this here is not the norm, so it's like it's a vector. So
Okay. In this line, we bring back the absolute value.
yeah.
Okay. Thank you.
Yeah. Okay. Yeah. Thanks for the question. So yeah, let me continue. And here, so in some, and also they introduce an extension of the previous architecture, in the sense that in some cases, the output depends not only on the position x, but also on the velocity v. For example, in the example I just described, if you want to predict the motion of the particle, and you just know its the initial position, you don't know where it will go. So you also need to input the initial velocity. So they introduce this like simple extension in the sense that it takes also the velocity into the input layer. And so the original formulation is like xil plus 1 equals to xil plus c times sum of j not equal to I, xil minus xjl times this. So so this is the original formulation, right? But if you want to take the velocity also into account, they just add another they add this thing here. So they want to update the velocity through this formula, and then they use the velocity to update the position. So this is kind of like a numerical integrator in some sense. So yeah. And also here, the sum of j not equal to I is actually not summing all the nodes, in the sense that they are just summing this j in a neighborhood of I. Yeah.
Jen, are this because the dimensions don't match, so the velocity here has some time step, I guess, suppose.
Oh, sorry.
I mean, you cannot just add velocity and displacements, so there must be some time. I mean, where is the from L to L plus 1? There's a time element to make it dimensionally correct.
I see. So you mean like you
the units are not correct.
Yeah, but I think the thing here is that so here the phi x is learnable, right? So you can like have like a learnable parameter like intrinsically embedded in this phi x. So like if you have a delta t here, it can be absorbed into the neural network. I'm not sure if I'm
if they just add this, is it velocity? You cannot add velocity to displacement.
Oh, here, yeah, this one, right?
Yeah.
I think this velocity, because this is vi L plus 1, I think maybe this is because of the notation issue, because here, as I just said, here the phi v and phi x are neural networks, right? So they actually not represent the vi, like that doesn't actually represent the velocity at the next time step. What they represent is delta t times the velocity at the next time step.
Probably, yeah.
So, and that delta t is absorbed into the phi v and phi x. So that's why so they can actually train successfully. So, but here maybe the notation is not very rigorous. So yeah. Okay. Yeah. So that's all for the neural network architecture. And here are some like simulation results. And they
can I ask a quick question?
Yeah.
In your previous slide. So this reminds me some sort of like momentum method that, because if you replace the VL plus 1 in the below, then the only difference between the original formulation and the new formulation is add some previous information, phi, v. So let me a little bit annotate if I can.
Yeah.
So this is the only part that has been changing. If you just plus adding these two here, right? Compared to the original, but the new formulation involves some sort of like previous information involving this interaction, so that do you know any work that somehow extends this idea to say, because this is seems to me that momentum method, then we have a Nesterov method as well, so that it seems to me it is quite plausible that incorporate some Nesterov information into it. So, so is this the, I just maybe my is some comment that I come up with.
Yeah, sure. Yeah, I got what you are saying. Like maybe some Nesterov type of yeah, but I haven't seen like architecture like that in literature. So maybe good to do a literature survey on that. So
yeah, thanks.
Yeah. So okay, thanks for the question. So yeah, that's for the architecture part. And so here is the simulation result. And in the first example that they show, is not on the it's not on the particle simulation. It's just on, so this is like a static situation, in the sense that you are just given the positional information of the molecule and you want to predict the chemical properties. So the input is the position X of atoms of a particle and the corresponding atom types. And this atom type can be is just the H. It can be added into the H, which is the latent, latent feature layer of nodes. And each molecule contains up to like 29 atoms. And the output is a variety of 12 chemical properties that are estimated per molecule. And they use 100,000 for training, 18,000 for validation, and 13,000 for testing. And here is the result, which they compare with a set of benchmark methods of graph networks. So most of these architectures are like graph networks and different variations. And here what they report is the MSE. So they claim that they can achieve a better MSE compared to most of the existing state-of-the-art methods. And also, like just to mention, like I think these molecular data are like experimental instead of like simulated. So that's why we need so that's why like it's very useful to use some data-driven methods to help us do the prediction, because like there is no governing equation or that type of thing in general for the experimental data. Yeah. And however, like this is not like the best in all cases. Like still in some cases, it's not not as good as some of the existing methods. For example, compared to the DimeNet++ here, sometimes I think it's in most of the cases it's not as good, but it beats a lot of the baseline methods. Yeah. And actually, like there is I just found on Twitter that there is a person that does do the simulation that is conducted in this paper using just 50 lines of code in Jupyter Notebook. So it's very interesting to see like how this simple idea could be implemented in such a simple manner using PyTorch. The only package that they are using is just NumPy and PyTorch. So it would be if someone is interested in this, it would be great to check it out. Yeah, so just like a very few lines of code. Yeah, and so here is the next simulation result, which is again like on a kind. So here this is not on the static data in the sense that we want to predict the motion of particles. However, this simulation is not on a very large data set, in the sense that they're just training on 5 body charged particles, which are governed, whose motion is governed by the Coulomb forces. So so they use 30,000 trajectories for training, 2,000 for validation, and 2,000 for testing. And each trajectory has a duration of 1,000 time steps. And they report their MSE and forward time with some of the existing methods in literature, and they achieve a better MSE. And here they also plot the MSE versus the number of samples that they use for training. to show that they are not like overfitting in the when we use more samples for training. Yeah, and that's for the 5-body problem, and they also apply this architecture. Is someone speaking?
Hi, Zhang.
Yep.
This is Thomas from MTSU group, but I'm currently in Ghana, Professor George. So I'm asking regarding the noise GNN.
Noise, let me, oops, can I, this one?
No,
or
the next slide, please.
Oh yeah, sure.
So my quick question is, does the noise, whether introduced into the model, affects the properties of the GNN, say permutation equivariance properties?
Yeah. So yes, so the noise here is important in the sense that they because like there could be like there is some like symmetry in the graph. So so they want this noise added to the input to break this type of symmetry.
Okay.
Yeah. Does that answer your question, or?
Yeah, it does. But I want to make a quick comment to Professor George. I'm here with a professor in Ghana, and he's also a numerical analyst person, and he's interested in joining your group, sir.
Thank you, Thomas. Yes, thank you.
Okay.
Yeah, thank you for the question. And also, and so for this graph embedding task, what they do is they apply the same architecture, but they want to do a graph embedding task. So what the task is just to like embed the graph, which embed the graph into some like latent dimension. So originally the graph which is described by the adjacency matrix, when the graph has m nodes, has to be described using a memory of m squared, because the adjacency matrix, the memory in total is like m squared. But if you want to map it into a latent layer, then you can, and you just store the node information where the dimension of the node feature is n, then your memory cost will be m times n. So if n, which is the dimension of the node feature, is much smaller than m, which is the number of nodes, then you can save a lot of memory in this type of when you are modeling a graph. So
this is actually what the work of Menja, right? The graph embedding. So they can go from like one of the 80,000 or 100,000 nodes, they can go down to dimension of 16 or 32 with the graph embedding. So you can save a factor of 1,000 actually. It's a huge one.
Yeah, exactly.
So it's a very good idea. I thought nobody had done it, but already people have done it. Okay, please go on.
Yeah, but the good thing is that here, I mean, for this paper, they are not doing it in a very good. I shouldn't say this, but I don't think like they do it very efficiently, in the sense that if you look at these numbers, where m is the number of nodes, it's like already very small. It's just like
that's very small. Yeah, that's
so if I understand it correctly, they are not like reducing the number of nodes. They are not reducing the graph by a lot. So because this is just like a test of how should I put it? It's like just test this idea. So
proof of concept. Yeah,
proof of concept. Yeah, exactly. So maybe we don't want to ask too much about it. So yeah, and so yeah, that's for this graph embedding task. They want to show like using this kind of equivariant type of graph network, they can do better than the traditional like a simple graph neural network. Yeah, and
hi John, can I ask a question?
Yeah, of course.
Yeah, in the table I see there's some error and F1 score here. So does that mean this graph embedding is set up is a reconstruction? I thought it was a reconstruction problem, right?
Yes.
And I see it. The input of the network is some random noise, right? Yeah, but my question is, in your previous example, such as the molecular dynamics or in the 5-body system, the input output should be something similar to positions or velocities, something like that. And if the graph neural network itself should be permeation equivariant, but it doesn't have any something like the equivariance you introduced today, such as translation or rotation invariant. And the new proposed network have these properties. But in this task, the graph embedding, it does have anything. It doesn't have any relation to positions or something like that. So how should we understand that the equivariance will help the simulation of graph embeddings or something?
Yeah, that is a very good question. Like, so basically, so I think, so I would say I don't like this experiment as that of the previous two cases. Like, so I don't see like there is like a very clear like connection between this translation or rotational equivariance as in the previous case. But however, like what they claim in the paper is that possibly like by adding this type of equivariant architecture, as you can see from here, like if your phi actually satisfies these two properties, then you automatically get some stability, right? So possibly that's why they can achieve a better result in this case, because like here it's like the scaling factor is like will be I think will be 1 if you enforce this architecture, so that you can your network is more stable in some sense. Does that answer your question?
Yeah. Okay. Thanks.
Yeah. Thanks for the question. Yeah. And okay, that's
Jen, that's a good point that you're making, that it's not just actually the symmetries that you expect. It's and most importantly is the stability for these systems that you know also from your genetic work, that's what happens, and especially when you extrapolate. So that's an important observation, I think.
Okay. Yeah. Thank you. So yeah, that's for the simulation results of the EN equivariant graph network. And they also propose an extension of the previous architecture into something called the EN equivariant normalizing flow. So the task here is slightly different from the previous one. So now what they want to do is not to predict the chemical properties or predict the motion of the particle, but instead they want to generate the particle. So this is like a generative model. So what they want to do is like they want to generate like convincing molecules based on existing experimental data in data sets like QM9, QM7. So they want to design this type of generative model to really generate these type of molecules, which could be useful in terms of drug design or like other applications. So what they do is they incorporate the idea of normalizing flow together with their existing equivariant architecture, in the sense that, so what a normalizing flow does is it takes your data, which is the x and h for the molecule in our specific task here. You take this as your input, and you first lift your node feature into a continuous space and map it together with x, which is a position of the molecule, through an invertible neural network to a Gaussian distribution. So you want to design an invertible neural network which maps your data to a Gaussian distribution. And the reason why we want this neural network to be invertible is because we want to do the sampling, in the sense that you can generate a random sample easily from this Gaussian distribution and map it back through the invertible neural network to really generate the data in the distribution, in the original distribution. So that is kind of like what the figure in second row shows, in the sense that you sample like something in in the Gaussian distribution, and you map it through an invertible, map it through the inverse of the invertible neural network to really generate a convincing molecule. That's a general idea. And the way people normally train this type of normalizing flow, specifically the continuous normalizing flow, which means that the invertible neural network is parameterized by a neural ODE. What they do is they have this type of change of variable formula for the probability density of the distribution. So this is the change of variable formula where X is your data, and Z is your embedding in the latent space, which follows the Gaussian distribution. And when you have this formula, which means that you can map your data to the Gaussian distribution through an ODE phi, you have their probability density connected by this equation on the left-hand side, where J is the Jacobian and TR is the Hutchinson's trace estimator. These together is the Hutchinson's trace estimator, which can be computed, which is already implemented in PyTorch. And assume that Z follows the Gaussian distribution, and since X is given as data, you can learn phi through this formula because you can minimize the negative log likelihood of phi because you already know what PZ is because it's a Gaussian distribution. And to generate samples, you simply sample a Z from the Gaussian distribution and solve the ODE backwards in time. Then you get like a sample of the molecule. And what they propose in the paper is the so-called EN equivariant normalizing flow. What they do is they don't use the naive neural ODE here as dxdt equals to phi x. What they do is they add some structure into it by using their equivariant graph network, in the sense that here is the ODE that they want to follow, where dxdt is equals to xl minus x, where and dhdt is equals to hl, where xl and hl is an EGNN on the input x, on the data x and h. So you map the x0 and h0, which is x and h in the data space, to those Gaussian noise in the latent space. Yeah, and that's the main idea. And then they also prove in the paper that through this kind of equivariant normalizing flow, we can preserve the invariance of the distribution, in the sense that we know that the Gaussian distribution will be rotational invariance. Then through this kind of mapping, you can also achieve the rotational invariance in the target distribution, which is desirable in some cases. And they show the simulation results on two specific data sets, on the called DW4 and LG13, which so the first data set is composed of 4 particles embedded in a 2-dimensional space, which are governed by an energy function that defines a coupling effect between pairs of particles with multiple metastable states. And the second example is the Lennard-Jones example, which are composed of 13 particles. So still, like, this is not a very large data set, but this is just for the proof of concept paper. So that's why it's just like some small data set. And also, like, this type of generative modeling, I don't see like too much, maybe because of my ignorance, I don't see like too much paper on this type of problem. So so I would argue like this is still like a good paper in bringing some new ideas. Yeah, and so energy functions of both data sets are equivariant to translations, rotations, and reflections. And they use 1,000 validation samples and 1,000 test samples. The training samples vary based on the, so as shown in the following table, where they train with different number of samples in the training data set from 100 to 10 to the power of 5. And they consistently outperform the state of the art in in the existing literature in terms of the negative log likelihood on the test set. Yeah. And they also show the simulation results on the QM9 positional dataset, which is a subset of QM9 that only considers positional information and does not encode node features. Basically, you only want to generate the position of the, you only want to generate the position of the particles. You don't want to generate like other chemical properties. So this is like an easier task. And it turns out that we can do this in a good way, in the sense that when you compare the relative distance distribution between their learned, with their generated data and the true distribution, you can see like it matches pretty well. And and also they also report the negative log likelihood and the JS relative distance with the existing methods, where they also claim that they can do better than the existing methods. And they also try to like implement, try to test their methods on the whole QM9 dataset, where they have both the position, they want to generate both the position and the features. But the results, I don't find it to be like very good, but they still like reported it in the paper, in the sense that here, even though the negative log likelihood is like, looks like small, but when compared with data in the data set, the percentage of stable molecules is 95%, but you can only generate like 4.9% of stable molecules, because when the way they regard a molecule as stable is like they want every atom to be stable. So it's like kind of difficult for a molecule to be stable in general. So that's why this number is too small compared to the data. But still, they claim that they can beat the like the state of the art in literature. Yeah. So below are just some like examples they generated using their methods, which are different molecules. So that's all for the simulation results. And here is a brief summary. So I just copy a paragraph from the DeepMind graph neural network paper that I show at the beginning. So they say like there are also natural ways to incorporate stronger generic physical knowledge into our framework, such as Hamiltonian mechanics and rich architecturally imposed symmetries. To realize advantages over traditional simulators, future work should explore how to parameterize and implement GNS, which are graph networks, computations more efficiently and exploit the ever-improving parallel compute hardware. So what they do in this equivariant paper is that they really impose some symmetries into the neural network architecture to make the to try to make the prediction of the graph networks better. And but at this point, their method is only tested on some toy datasets for simulation tasks. I mean, I'm not saying like QM9 is the toy dataset. I'm just saying like for the 5-body problem of a charged particle, like it's not a very big dataset. So still we need to check whether it outperforms the state of the art on like more complex datasets. So basically, it means that there are still a lot of things that can be done in this area on more complicated scenarios. And maybe other symmetries can also be added. For example, like symplecticity or other kind of symmetries can also be added. And maybe some application of the scenarios of the generative models maybe we can have some more applications of these kind of generative models, which I don't actually know too much about, and I'm open to discussions in all these kind of areas. Yeah, that's it for my presentation, and I can take questions.
Hi, Zhen. I have a question actually. So in the second paper, you discussed like they go from discrete molecule to Gaussian distribution that, yeah, lift to continuous. I was wondering like how is that? Yeah, how it was implemented and how plausible that should be.
Yeah, that is a very good question. So what they do is like they use so first of all, I think like I didn't I didn't fully understand the details of this lifting to continuous procedure, but based on my understanding, it's like they use a neural network to which they parameterize as Q here, which maps the discrete vector H to like this italic vector italic H, and they use some sort of variational encoder type of architecture to achieve that. But I'm sorry, I haven't like gone into that detail, but we can discuss like maybe after this. Does that sound good?
Zogren can help you with the normalizing flow.
Yeah, I'm pretty familiar with dominant flows.
And also Midland presented a paper before on that, but Zogren is working on normalizing flow.
Actually, aside from this question, I also have another one, because it's like I feel the idea that it's reversible or like invertible something is quite fascinating, and we kind of also saw a similar paper called, I don't know if it's that similar, but it's called the Boltzmann generator.
Yeah.
Yeah, I don't know if they share a similar idea, but it sounds like similar to me.
Yeah. So the Boltzmann generator is the one that you present in the quant seminar, right? Like
yes.
A few hours ago. Oh yeah, okay. I think there are some similarities there. I don't remember if they use normalizing flow, but I think like if you use normalizing flow, then it has to be in most of the cases, like the neural network has to be like invertible, because you want to like do the reverse, do the sampling. So
yeah, I feel that paper gives me a stronger motivation of doing this invertible, but this one I didn't quite get that.
So like.
Zhang, Jen, do you remember how they did the invertible? The main different ways. There's something called invertible networks. In when Midland presented, I think he showed the structure. I forgot the exact structure now.
Yeah.
Do you remember the invertible neural network, which guarantees that it can always invert it? Midland probably went for lunch.
Yeah.
No, I actually can send you the paper.
Okay, but do you remember the structure of the
it's a very special type of structure, so it's not a fully connected network. So there are many there are different types of invertible network, but they're crafted sort of so that the network is invertible.
Yeah, I remember for the first version of the invertible network, they basically apply a math trick here. So let's say if we have input X, we try to go from X to output Y to be invertible. Then they first do a copy of X. Then they apply a few math equations. I don't know exactly, but a few tricks, math tricks to make sure, okay, basically by copying actual information, then do some transformation. Then we can go from Y to the left, go to the X.
Yes. Yeah, I remember like there are like quite a lot of invertible neural networks papers, like including like the so-called NICE, basically NICE, which like use the upper and lower triangular matrix to realize this type of invertible property. And but here like they are just using like an ODE solver, which like is intrinsically reversible.
With the adjoin method, use the adjoin method to cut the cost. Yeah.
I was wondering.
Nominal flows are invertible neural networks.
Yeah.
And they're they have stronger assumption that their Jacobian should be easy to compute. So like not every invertible neural network can be nominal flow, but every nominal flow is a neural network. It's invertible neural network. Yeah.
I see. So it's like a subset, right?
Right.
Yeah.
Yeah. Is there any like a good paper that you would suggest about the specific, like the paper introducing how to design this invertible neural network?
Yeah, I know a few that I can send to you, but maybe like Minglang or Zhongren or Lu can also like share some of the.
Yeah, I would appreciate. Thanks.
Sounds good.
Yeah. Do we have any more questions for Zhen?
Everyone for coming, and thanks, Zogren, for hosting.
No problem.
Take care,
Yeah.
everybody. Stay healthy.
Thank
Hi,
you.
Professor George.
Hi.
And this is Dr. Mo from Ghana.
Hi, welcome. You're welcome
Thank
to join
you.
us every week. Yeah. Bye-bye.
All right. So I'll send a message then.
Yes, please.
All right.